I used to teach here a few years ago, and then retired, but I always enjoy fractals, and I thought today would be great because you're doing Fractal Week to talk a little bit about fractals. I have a video that I'm waiting for Adobe to load here in a few minutes, and then we'll run that to do a little introduction. I have a little, it's not much of a handout, but it gives you some websites that you might be interested in. So I don't know, is everybody in here for fractals? Sometimes people use this room for labs. I don't, if I run out, I'll just ask Billy Joe. Oh, yeah, that's a good idea. It is. Okay. So, how many people love mathematics? You all should raise your hand, right? You didn't raise your hand. Let's see, your bride. You should love mathematics. Okay, all right. I won't tell your grandfather. Yours either. Same guy. It's a computer. How you doing? Find the reason why people are using that. A chair? I don't know if I'm gonna. Somebody might hit this. Maybe. I got a few. So what I'd like to do is, if this works fine, we're going to do a little introduction. It'll be about 8 to 10 minutes. It comes from a PBS special, Nova, on hunting the hidden dimension. But it's a great introduction to fractals. So I'm going to try to run it here. Hopefully the volume, last time I was here, it worked fine, but I'm sure these math teachers will help me figure it out. I don't hear any volume here. Do you, George? Right? Do something different.
Wireless communications.
I'm hearing something.
One of nature's biggest design secrets has finally been revealed.
My God, of course, it's obvious.
It's an odd-looking shape you may never have heard of, but it's everywhere around you. The jagged, repeating form called a fractal.
They're all over in biology. They're solutions that natural selection has come up with over and over and over again.
Fractals are in our lungs, kidneys, and blood vessels.
Flowers, plants, weather systems, the rhythms of the heart, the very essences of life.
But it took a maverick mathematician to figure out how they work.
I don't play with formulas, I play with pictures. And that is what I've been doing all my life.
His was a bold challenge to centuries-old assumptions about the various forms that nature takes.
The blinders came off, and people could see forms that were always there, but formerly were invisible.
Making the invisible visible, finding order in disorder. What mysteries can it help us unravel? Coming up next on Nova, hunting the hidden dimension.
I'm hoping we don't have to go through the commercials. You never know.
Mandelbrot graphed the noise data. What so surprised him? Regardless of the time scale, the graph looked similar. 1 day, 1 hour. It didn't matter. It looked about the same.
That's got 3. I want 2.
It turned out to be several dimensions.
We are approaching what astronomers on Earth call the local group. 3 million light years across, it contains some 20 galaxies. It's a sparse and rather typical chain of islands in the immense cosmic ocean.
There's the one.
1978, at Boeing Aircraft in Seattle, engineers were designing experimental aircraft.
Exotic things with two wings or two tails or two fuselages, just weird stuff. Because who knows, it might work.
A young computer scientist named Loren Carpenter was helping them visualize what the planes might look like in flight.
I would get the data from them and make pictures from various angles, but I wanted to be able to put a mountain behind it because every Boeing publicity photo in existence has a mountain behind it. But there was no way to do mountains. Mountains had millions and millions of little triangles or polygons or whatever you want to call it, and we had enough trouble with 100, especially in those days when our machines were slower than the ones you have in your watch.
Carpenter didn't want to make just any mountains. He wanted to create a landscape the planes could fly through. But there was no way to do that with existing animation techniques. From the time movies began, animators had to draw each frame by hand, thousands of them, to make even a short cartoon.
That's why they call me Thumper. They call me Thumper.
But that was before Loren Carpenter stumbled across the work of a little-known mathematician named Benoit Mandelbrot.
In 1978, I ran into this book in the bookstore. Fractals, Form, Chance, and Dimension by Benoit Mandelbrot, and it has to do with the fractal geometry of nature. So I bought the book and took it home and read it. Cover to cover, every last little word, including footnotes and references, twice.
In his book, Mandelbrot said that many forms in nature can be described mathematically as fractals, a word he invented to define shapes that look jagged and broken. He said that you can create a fractal by taking a smooth-looking shape and breaking it into pieces over and over again. Carpenter decided he'd try doing that on his computer.
Within 3 days, I was producing pictures of mountains on my computer at work. The method is dead simple. You start with a landscape made out of very rough triangles, big ones. And then for each triangle, break it into 4 triangles. And then do that again, then again and again and again and again.
Endless repetition. What mathematicians call iteration. It's one of the keys to fractal geometry.
The pictures were stunning. They were just totally stunning. No one has ever seen anything like this. And I just opened a whole new door, a new world of making pictures. And it got the computer graphics community excited about fractals because suddenly they were easy to do. And so people started doing them all over the place.
Carpenter soon left Boeing to join Lucasfilm, where instead of making mountains, he created a whole new planet for Star Trek II, The Wrath of Khan. It was the first ever completely computer-generated sequence in a feature film.
Fascinating.
Made possible by the new mathematics of fractal geometry. Benoit Mandelbrot, whose work had inspired that innovation, was someone who prided himself on standing outside the mainstream.
I can see things that nobody else suspects until I point out to them. Oh, of course, but they haven't seen it before.
You can see it in the clouds, in the mountains, even inside the human body.
The key to fractal geometry, and the thing that evaded anyone until really Mandelbrot sort of said this is the way to look at things, is that if you look on the surface, you see complexity, and it looks very non-mathematical. What Mandelbrot said was that think not of what you see, but what it took to produce what you see.
It takes endless repetition, and that gives rise to one of the defining characteristics of a fractal, what mathematicians call self-similarity.
The main idea is always that as you zoom in and zoom out, the objects look the same.
If you look at something at this scale, and then you pick a small piece of it and you zoom in, it looks very much the same.
The whole of the fractal looks just like a part, which looks just like the next smaller part. The similarity of the pattern just keeps on going. One of the most familiar examples of self-similarity is a tree.
if we look at each of the nodes, the branching nodes of this tree, what you'll actually see is that the pattern of branching is very similar throughout the tree. As we go from the base of the tree to higher up, you'll see we have mother branches and branching then into daughter branches. If we take this one branch and node and then go up to a higher branch or node, what we'll actually find is again that the pattern of branching is similar. Again, this pattern of branching is repeated throughout the tree, all the way, ultimately, out to the tips where the leaves.
Okay. I have an EDD, it's called The Amazing Mandelbrot Set, and it's got some neat stuff I want to reference in a minute. Oh, look, the lights came on out of it. So, how many people are familiar with fractals? Have you ever heard of it before? Okay. So, that's a good introduction. If you really want to get into the whole fractal thing, that whole series, it's about an hour. It's a Nova PBS special. Really neat stuff that they're doing with fractals. And actually, they're doing more stuff in fractals now than they've ever done before. Have you ever heard of a fractal antenna? A fractal antenna is being used in your cell phone now because of the design that they can create. It's used in biology and medicine and obviously in landscaping for graphics, arts, and all sorts of stuff. It's one of the most current topics in mathematics there is. So what I'm going to do today, I don't know what that is talk a little bit about fractals. And the one I like the most is the Mandelbrot set. But first let's start off, what is a fractal? I don't know if you can see that. It's go up higher, but I want to keep that open too. Sorry, I'm having trouble with the technical difficulty. Okay, while I'm waiting for that to come up, a fractal is a rough or fragmented geometric shape that can be subdivided into parts, each of which is at least approximately a reduced size copy of the whole. That sounds pretty complicated, but the things that are kind of neat are the fact that they're self-similar. I mean, they look like the same, like the guy said on the video, that if you blow it up, it looks like you have the same object you started with. And it's independent of scale. In other words, it doesn't matter how far you blow it up, you're going to see the same object again. So that's two of the neat things about a fractal. One of the fractals that you may have seen, I don't know, in one of your math classes. Anybody ever seen a Sierpinski triangle? Yeah? Sierpinski triangle? Okay, now the Sierpinski triangle is one of those things that's a fractal because it repeats. If you zoom in on any one part of this, you'll see it's the same thing as what you started with. And you keep zooming in. And you can repeat it on to infinity. And it looks pretty neat. So that's an example of a fractal. How about the Koch snowflake? Ever heard of that? It's another example of a fractal. And what happens is you start out and you do something with a straight line and you do little zigzags there and you repeat it over and over again. It just multiplies and it ends up looking like a snowflake. Again, it has the two properties that we talked about, self-similar, and no matter how much you blow it up, it looks the same. Now the one that I'm going to do the most work with is called the Mandelbrot set, named after that guy that was on the screen, Benoit Mandelbrot. Anybody know if he's still alive? unfortunately. He just died last year. So he's a relatively new mathematician in terms of some other mathematicians. Can you name a mathematician? Oh, this is going to be good. Can you name a mathematician other than Benoit Mandelbrot? Anybody? No? Who? Isaac Newton. Now, when did he live? 1700s, right? So Benoit Mandelbrot lived in the 1900s, right? So he's a relatively contemporary mathematician compared to what's been before. Now, Mr. Mandelbrot came up with this thing, this diagram, which is supposed to be, what were the two things again? What were the two things that we said a fractal had? Anybody volunteer? I don't know. In the back?
It repeats itself.
It's self-similar, it repeats itself. And what was the other thing? Independent of scale. That means that if you blow it up, you get the same thing back. Now, the Mandelbrot set isn't exactly, if you blow this up, you just go in one section. It looks like maybe this section here, if you turn it this way, it might look, you have to play with it a little bit. But it does happen that if you blow it up, you will see the same shape. And that's really some fascinating things about it. Now, here's the technical definition of what a Mandelbrot set is. It's a visual representation, another fancy word for graph. It's a graph of an iterated function, get too technical here, on the complex plane. So, in order to understand what I'm going to talk to you about in the next 10 minutes, you sort of have to have some idea of what an iterated function is in the complex plane. Plane. So, let's see. A function. You've seen those, right? Some of you, not all of you, but some of you. What is a function? Well, a function means you put something into, well, in most cases, a mathematical operation, and you get an answer that comes out. We call that a function. And there's some technical definitions we're not going to get into. We usually use f of x for our function, right? Shake your head anytime you want. That's good. Okay, so we sometimes say f of the input gives me the output. These are all terms that you might have seen. We sometimes write the function as a mathematical equation, f of x equals x plus 1. That's just an example. It's not the only function. So if I took a number and plugged it in for my input, I should get an output. For example, if I plug in 0, I get 1, right? 0 plus 1. If I plug in 1, I get 2. That's a pretty boring function. But that's what a function does. You just plug in numbers and you get an output. Does that make sense? Okay. Now you will notice that this particular, what I did here, is I took the output and plugged it back in for the input, right? That's what we call an iterated function. You take your answer and plug it back into the function, and you keep going. And we see what happens to the value as we keep iterating, repeating. Okay, so another example of a function. I'll try to go a little faster on here. Here's another example of a different function. This is this x squared plus 1. So again, I'm going to start with 0. I plug it in, square it, add 1, I get 1. I take that answer, plug it in there, and repeat. That's the iterated part of the function. I just keep going. So far, so good? If it's too confusing, I'll give you an example of on the website that you could go through and step by step. Okay, so now we're going to talk about the Mandelbrot function. The most amazing thing that got me excited about Mandelbrot is that whole diagram of the Mandelbrot, and we'll see some fancy pictures there, is all generated by this function right here. X squared plus c. It's just phenomenal to me. That all the multicolored pictures that you see of a fractal, or even these fancy designs that you see here, are all generated by that simple equation, x squared plus c. Now c is, we're going to call it the initial point, and we're going to start out and say, let's suppose the initial point is 1, and then we're going to do the same thing we did with every other function. We're going to iterate it, plug it in, get an answer, plug it in, get it, and so forth, depending on what value of c you pick. Now, C is going to be important if you really want to understand the Mandelbrot set. All right, so let's suppose, let me ask you one question here. what do you notice? You may not even notice that, but if C equals 1 and I started with 0 and plugged it in this function, what would I get if I plug in f of 0? If I plug in f of 0, I get 1. And then I take that answer and plug it in, I get 2. And then I plug 2 in, I get 5. And so what happens is the numbers keep getting bigger, right? It doesn't look like they're ever going to get smaller. They're just going to keep getting bigger. All right, so if I take a small number, like 0.1, and do the same thing, start out with 0, plug it in, 0.1 squared plus 0.1. Now notice that C is 0.1. And I plugged 0 in and got 0.1, and then I got 0.1 squared. Now what happens to the answers? Are they getting bigger?
Yes.
A little bit bigger, but not as big as they used to be. In fact, I don't want to use a fancy term here, but the numbers appear to sort of flatten out or converge to a number. They don't go way off to infinity. So that's pretty important, that numbers that are small, now when I'm saying small, they're between 0 and 1, they seem to get smaller or converge to a smaller number. If the numbers are bigger than 1, they seem to get bigger and bigger, right? Okay. So what happens is, if I can get this DVD to work, right? That's the game. Yeah. All right. Let's see if I can get back to the main menu. Okay, good. Okay. So, if I can advance slowly. That looks familiar. And we're going to skip through here a little bit because I want to get to the part. So there's an example. Is that big enough? Everybody see that? Okay. Now, hope I can pause that. Whoop. Go backwards. So what happens is if you pick a number 1 or bigger, you plug it into x squared plus c, it's going to go to infinity. It's going big, 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 right? Does that make sense? If you pick a number between 0 and 1, it gets smaller or it converges. It doesn't get smaller. It converges to another number between 0 and 1. Now, we didn't really talk about these numbers, but with negative numbers, you get some interesting things happening. Because when you square a negative number, it becomes positive, and then you add to a negative. But what happens is it starts bouncing around between 0 and negative 2. Let's see this. So weird stuff happens between negative 2 and 1. What do I mean by weird stuff? Well, it turns out that that picture you see up there. Let's go back to this one. Let's see if I can freeze that right there. Right there. I think it's paused. Okay. So notice that it looks like the Mandelbrot set is sitting between, actually it's between a circle between negative 2 and 2. And points that are in between negative 2 and 1 do all sorts of interesting things. But we want to classify those points and how long it takes them to get big. So the Mandelbrot set, keep going here. It can't be right.
Well, what you just had up there, because it had 1 in the Mandelbrot set, or 0.9 in the Mandelbrot set. That's not right, because if you square 0.9, you get bigger and bigger. Add another 0.9, you square, you're well past 1, and then you're past 2.
But past 2, right. Hang on a second. We're in the complex plane. Okay, so we're saying that between negative 2 and 0, things do something different. And I'm going to try to move that past that. And they're kind of neat between negative 2 and 0. They sort of bounce back and forth. So now we need to talk about the complex numbers and the complex plane. Okay? So first, let me stop this for a second. Anybody know what a complex number is? How about an imaginary number? It's in your mind. Well, you don't really have to worry about it too much. But imaginary number is based on I. Anybody know what I is? Definition of I?
Root -1.
The root of -1. It's the square root of -1. Again, don't be too concerned if you don't really know all those definitions. But Mandelbrot set is based on the complex plane in a complex number system. And again, you might not be able to see all that very well. But in a complex number system plane, you have the real number system on the x-axis, okay? And you have the complex numbers on the y-axis, okay, down this way. So if you wanted to find a point in the complex number plane, you have to give it a real part and an imaginary part. So let's say this is 1 plus 2i. It's over 1 and up to 2i. So that's how we plot numbers in the complex plane. Not a big deal. I mean, it's not really that hard to figure it out. But the interesting part is that if you understand the properties of I and how to square it, and you plug it into x squared plus c, things get pretty interesting. So, they take their time on this one. So they talk about -1. And you can see this particular video online if you want. If you want to look at it in more detail. So now we're going to take x squared plus c, which I told you was the foundation of a fractal, of the Mandelbrot set, not a particular fractal. And we're only going to look at between -2 and 2. Okay? So if you took a number like 1 plus I, and you squared it and added it to 1 plus I, and kept iterating it, you'd have to know a little bit of mathematics about I and I squared and all that. But it's not that hard to calculate, and certainly a calculator or a computer can do it very easily. What we're trying to do is to see whether the number gets bigger or smaller, or does it converge to some other number. So it goes through this calculation. We'll go through it faster than that. Whoop. Now we'll pause. Now, all of a sudden, we have a color here. And this is where it becomes very interesting on the Mandelbrot set. So all these numbers in red, now this is from -2 to 2, okay? And -2 to 2. The numbers in red are the ones that got real big after one iteration. Okay? Now, what do I mean by real big? So somebody had to arbitrarily say, what's real big? And they decided to come up with bigger than, I don't know, magnitude of 2. It's not a really, but it's pretty obvious that when it gets to that size, it's going to get bigger and bigger. So all the numbers in red get very big quickly after one iteration. And an iteration means you plug it into the function and you get an answer, right? And if it's big, we put it in the red division. So if we keep going, whoa, we jumped quickly. Well, we went pretty fast. So what's happening when you do 20 iterations is every color relates to how long it takes to get big, whatever big means, which I said was bigger than 2. But, so it gets really complicated in the Mandelbrot set when you start doing different colors for how long it takes to get big. Okay? So these colors are arbitrarily set. Somebody says, I like red to be the first iteration, I want green to be the 2 iterations. And it's an arbitrary thing. So you can get different shapes and colors and whatever you want. But the fascinating thing about the Mandelbrot set, due to computers, we can zoom in on these fairly complicated parts and do an iteration and then keep talking about, well, how long did it take to get big? And do different colors on it. So, now we're going to go to the part where you can play a little bit. We're going to go look at, and I think you can all go to Internet Explorer there. So if you click on Internet Explorer there, we'll see if we can get to a website. There's a couple different ones. I was hoping the one I use, you have to download and sign in and all that. We're going to use a different one here. If you look at my handout and go to the third page, I believe, it's fractal generator websites, different places where you can generate fractals. So if you go, let's try the first one that says www.coolmath.com. Okay? So up here in the edge, did you get one? I got extra one here. Did you get it? Coolmath.com. Probably fractals. Probably.
Oh, I like the numbers and calling them out.
I don't know if that's going to work. I'm trying to shortcut it with the fractals. So if you type the whole thing about fractal generator, you can see some different, create your own fractals. Okay, so I'm waiting for you guys to get into this fractal generator. How you doing? Anybody having problems? You got it? Okay, so what we're going to do, it says to use this particular fractal generator, drag your cursor to create a box and zoom in on part of the fractal. So, if you take your cursor and you hold it down, and you say, I want to go into that section of the Mandelbrot set, and you click on it, you let it go, it zooms in. Okay? And then you just keep doing that, and you say, well, I think it's pretty interesting in here. Let me go in there. And you click on that, and then, oh, you might go in here. No, I don't know. Maybe we want to do this section here. So what you do is you start playing with the Mandelbrot set. Now remember, the Mandelbrot set was generated by a really complicated equation, right? What was that equation? X squared plus C. One simple equation called x squared plus c gives you this unbelievably complicated looking document, or picture. So your goal, I guess during Fractal Week, is to download one of those fractal generators, right? This is one. I like a couple other different ones. There's Fractant, which is but you have to, it takes up a lot of memory, and I didn't want to play with it here in the lab here, but Fractant is another one. XAOS, I like that one, but you have to log in and you have to get a password. So if you look through that one, that's a little more sophisticated, and it's a lot nicer, I think, XAOS. Jason, is that Jason? You have a site, right? What's the Hypothesis? It's not a site, it's an actual program downloading the computer. Okay, what's it? Hypothesis, APOPHYSIS. So if you search for Hypothesis, he says that's a great fractal generator program. So what we'd like you to do during the week is to play around with the Mandelbrot set, find a nice looking picture or something that you think would be kind of neat, and then we'd like you to print it on an 8.5 by 11 sheet, submit it to the Math Learning Center, and then put a number on it, and then I guess your name will be on the back or something, and then people will decide what they think is the neatest.
This is Peninsula's excellence that we have.
Which one? He already has the best picture. So he might be right. I don't know. Now this video I have, it's called The Amazing Mandelbrot Set, and I will leave that for you because it's got some neat animated, not animated, but pictures of the Mandelbrot set. And I'm hoping I can bring it up again. I'll show you, give you some examples on that. Maybe. So I'm waiting for that to load up. I probably lost about half of you, right? Anybody have any quick questions you think I can answer? No? You doing okay? You finding the You making some fractals, you generating them? No, I haven't worked with scripts. This particular part of this they didn't like that. Well, I'm going to try. I was going to show you some neat animation with the fractals and things like that. So, does everybody understand what you're going to do? You're still playing, well, that's good. So you're going to find a fractal, one of these fractals generator sites. You can do it at home. You can do it here. If you find one that you want to print in color, where'd Brad do that? Didn't Brad do that? Brad printed one, but I thought he brought it up here. If you find one you'd like to print in here, they'll let you print one per student, right, Rich?
Right.
Color copy.
Go ahead and... Yeah, it's going to be sent across the hall to the color copier. We'll be able to pick it up and enter it into the contest for you. So. Okay. The catch to that is there's only one machine that we can print from, and that's the one where Mr. Fielder is sitting at right now. So you'll need to get that onto a thumb drive or something like that, where you can then bring it up there and print off that one machine. Okay. If you have access to your own color printer, you can do it that way. Or Aline Hartnett, director of the Math Learning Center, said that if you have no other way to print it, she's got a color printer you can use. Okay. So hopefully you have one way or another to be able to get a pretty good looking picture.
Yeah, like DVDs. Let's see. So let's see if I can generate one and show you how to picture generator.
I love that three-dimensional carpet. Yeah, it's cute.
All right. Oh, okay, so if you were doing it on this particular, and you found a picture you like, and again, I must tell you that some of the other generators are much more interactive as far as color and giving you some better resolution, but you can save the picture. Maybe. Oh. Oh, maybe not. Just keep through. Okay, so you would copy the picture. See, it says save picture. Yeah. So if you clicked on that, save picture as. And then you would probably save it to your, in this particular case I can save it to the desktop, but if it was yours, you'd probably have to save it to a thumb drive, right? So you would have a thumb drive, you'd save it to your thumb drive, and then you would come here and print it here. Now in this particular case, I can just save it to the desktop and save it, okay? And then you would print it, and how do you do that, Rich? You up here at favorites?
Why not just go to the desktop?
There was a print option.
Go to the desktop. You just save it to the desktop.
Right. Oh, just click on it, yeah. So where is it?
Right over there in the first row, or the first column.
First column.
Up.
Ah, there it is. So if I just double click on that,
And then,
right click,
yeah.
print picture.
Gonna be a good size one now?
I don't know.
I think it probably will.
So then, when you say print, you have to make sure it says this one. Phaser, Xerox Phaser 6G flat.
All right, you gotta select that printer.
You have to select that printer,
I can help you with that if you wanna try to get it correct.
and then when you click print, it should, but this is the only, so
Oh, you believe
Let me see if that printed.
you can try.
Oh, there's another one there.
The neat thing about, I don't know if you can see this as well, but this particular program, I don't know if you noticed this, but it's pointing to different parts of the Mandelbrot set, and it gives it a name, so that they have a whole bunch of pictures generated from that particular area. So if I click on, let's say, the sorcery one right in here, it will give me fractals generated from that particular section. So I'm going to click on sorcery, and now what's going to happen is it's just going to zoom in on that particular point.
It printed, but it came out small.
You got to make sure that when you print it, it's 8.5 by 11 or.
Did you check preferences?
Yeah, the preference. Ooh, that came out sharp.
This is also counted activity number 1.
Activity number 1.
No.
Or I mean 2, whatever. No.
So how are we doing? You okay with it? You understand what we're talking about with fractals? And there's some neat stuff. I will leave the,
Okay.
I've got some books here that I'll leave with the Math Learning Center, just little ones that are kind of easy to understand. Graphics, fractals, a graphing guide. Neat things about in here is it talks about the different applications that are involved in fractals today. Striking oil. They're talking about using fractals to help decide where you should drill for oil. The fractal antenna, fractal ecology, crowd control, all sorts of neat little things that are applications. I also have another book that you might be interested in, a little more technical. It's got talks about some neat mathematical principles that you might be interested in that one. And again, I will leave the fractal. You can just watch different parts and decide. Okay? Anybody have any questions? That's it. Thank you for coming, and hope you have a good time studying fractals and finishing it.